and start the recording. Happy Thursday. Welcome back to school. Only one more week until spring break. Then we get a little bit of a reprieve. What I'm actually doing over spring break is teaching still. I signed up to give a workshop for APA on clustered multi-level models, 2 90-minute workshops, which are free. So if you're interested, I can send you the information, or I may just send it out in an email anyway, because there's other free workshops that are happening this spring. A missing data workshop by Craig Enders that will be later in, I think, either April or May, and there's one or two beyond the ones that I'm doing. So free is good, right? Free is always good. By the way, workshops that you attend like this, those go on your CV. Additional training, that's a section. So you should have, and not necessarily your coursework, but like a description of like what models you've gotten training in, and so workshops and class material can kind of go in that. So I attended a lot of workshops when I was a graduate student and a postdoc, and I found those to be very useful. So hopefully you can make use of those resources. We have, let's see here, homework. I just updated grades this morning. Homework 2 went well. I feel like it was pretty good. As with homework 1, not everyone finished it on time, so I can't talk about it with the group. But if you have specific questions about what you missed and why, I am happy to talk to you about those. The population model, for those of you who are curious, that generated all of your data sets, the storyline was publication history doesn't matter as much if you have high quantitative training. That was the story that generated all of your data sets, because it's a true story. I believe it to be a true story. But learning quantitative methods can help you actually improve your publication history, because then you have more tools at your disposal to try and disseminate your research with. So next homework is not yet available, but the next thing you have to work on is another formative assessment due Monday. And you should be able to answer all of those questions already. Those are about categorical data models. So we just have one more part of this handout for 2B left, and then we'll finish with that. We have nominal left. That's the only one we have. So any questions on logistics or things I might be forgetting otherwise? No? Fair enough. So we finished with ordinal. And when I say ordinal, what kind of link function am I talking about? Logit? More specifically? Cumulative, yes. So we're in logits in this unit, but there are 3 different kinds that one can use for categorical data. Cumulative is what lends itself to an ordinal outcome. So that's where we have binary submodels. If I have C categories, I need C-1 binary submodels. And what makes it cumulative is in every binary submodel, we're using all of the answers. So that's the 0 versus something greater than 0. 0, 1 versus something greater than 1. 0, 1, 2 versus something greater than 2, and so forth. So every submodel uses all of it. That's cumulative. That's appropriate if you have an outcome that is undeniably ordered, and you're thinking of it as more means the same thing as you move up the scale. The middle ground one for partially ordered, or you're not sure about the ordering, is what's known as an adjacent category link function. That's one that would be like 0 versus 1, 1 versus 2, 2 versus 3 as the submodels, where you're only using part of the responses for each one. That one to me seems a lot easier to understand, but for whatever reason, it's very uncommonly used. The third one is the one that we have left, which is what's known as either a generalized logit or a baseline category logit. It has a couple different names. Nominal is the word that you would remember this with. Also known as multinomial, but that refers to the conditional distribution, not the link. So this is the one that we have left. The link function in nominal is essentially taking your outcome and creating dummy codes for it. That's how you make the submodels. So you designate one of your outcome categories as the reference, and the binary submodels give you the logit of the probability of answering in each of the other answer categories relative to the reference. So in this context, I'm still working with the same variable of likeliness to apply to graduate school, no, or very likely, but now I'm going to treat it as nominal, as a demonstration. Because I only have 3 categories, I can make the middle category the reference and make it directly comparable to our previous models. So the link function then in this case is if I put option number 1 as my reference, the first submodel is going to give me the logit of answering a 0 instead of 1. The second submodel is going to give me the logit of answering a 2 instead of 1. So the first submodel's coefficients are going to be backwards in the sense that 0 is less than 1 in this ordinal scale. But we can compare them to our nominal or ordinal model because if we switch the direction of it. So I'll show you what that looks like in just a second. So these results can be a little bit tricky because we have to put the submodels back together again to figure out what the overall probability is. So the first submodel is only using people who answered 0 or 1. People who answered 2 are not in it at all. The second submodel is only using people who answered 1 or 2, and the zeros are not in it at all. Nominal models default to having different slopes for each submodel. So you don't have to worry about proportional odds or constraints or anything. It defaults to having everything be different. So you'll have as many parameters as you have submodels, basically. Okay, with me so far? Yeah. So first step, empty model, figure out what's being predicted. You can end up with intercepts or thresholds in these as well if you're not careful, but for whatever reason, intercepts are far more common. Briefly, what's the difference again? What's an intercept and what's a threshold? Vocabulary drill. Do I hear someone talking softly, or is that someone out there talking? Anyone out there want to tell me what an intercept or a threshold is? No? No? Okay, someone take the easy one. What's an intercept? These are softballs. Yeah, the predicted outcome when all the predictors are 0, which in this case would be the 1, right? The higher category. So the intercept gives you the logit of the higher category at predictor levels of 0. So what's a threshold do? The lower one. Yeah, the threshold is the logit of the lower category response when all the predictors are 0. And how do I get back and forth? Yeah, times minus 1, the additive inverse. I've learned from the math people, that's what that's called. There's a name for times minus 1. Yep. So, cough, cough, homework question. In your next homework, which is not yet available, which means you'll have to get something else done instead for now, I will ask you for the predicted logits for higher categories and lower categories to remind you that if you go from one to the other, you don't need a separate model. It's just minus 1 to get back and forth. All right. So for in this world, though, we're going to do intercepts. The key is trying to keep track of what is the reference and what is the alternative, given this coding scheme. So the first submodel, for instance, is going to give us the logit of answering a 0 instead of a 1. So it's predicting 0 as the outcome of the first submodel, only in people who answered 0 or 1. So I can convert that into a probability, e to the model over 1 plus e to the model, just like usual. The second submodel is going to tell me the logit of answering 2 instead of 1, and I can convert that separate intercept into a probability the same way. So in terms of my notation, the second subscript is keeping track of the submodels, and I've named them 0 and 2 because that's what they're predicting. You're allowed to do that, by the way. You're allowed to go out of order or to pick different letters besides I and J for your subscripts. You are allowed. So this is helping me remember what the submodel is predicting. It's predicting 0 instead of 1. The second submodel is predicting 2 instead of 1. I picked 1 because it's in the middle, but you get to pick whichever one you want as your reference. So to do this in software, we're going to go mlogit in Stata, which is a built-in package. Don't need a special one for this. The option base outcome, can you guess what that does? Yeah, it says, which one would you like to be the reference? Well, I would like option 1 to be the reference because my options are coded 0, 1, 2. Do you remember how many people are in each category? Let me back up to the descriptive table that is our answer key for what the models are doing here. I should have put it back. I think I did put it in there, but I'll back up just for now anyway. This table right here, frequency table. This is our hope for understanding what the models are doing. So the proportion of people who answered a 0 is 0.55. The proportion of people who answered 1 is 0.35. And the 2s have a proportion of 0.1. Okay. So. Here we go. Back to nominal now. So the first submodel is giving me an answer for coefficient of 0.45. What's that? First off, is it a logit or a probability or an odds or what? It's a logit. It's hard to tell because 0.45 could be like any of them, right? It's a logit. This is an empty model, so we don't have to worry about when the predictors are 0 because there aren't any. What is this telling me? The logit of answering 0 instead of 1. Yep. Likewise, this logit, what's it telling me? Yes, it is. And these are logits, but I can back translate them into probabilities. And when I do that, the first answer corresponds to a probability of 0.61, and the second corresponds to 0.22. Neither of those numbers were in my frequency table. So the first time that I ever tried to do this, I was like, what the hell? Like, one of these has to be 0.5. Like, that's how this should work. No. Remember the part where this isn't cumulative? So only people who answered 0 or 1 are in the first submodel. So that means that of the people who answered 0 or 1, 61% of them answered 0. Of the is the idea of a conditional distribution, right? We took out the 2's. If the denominator for what total is only the people who have a 0 or 1, then this logit is translating into a probability of 0.61 for the proportion of people who answered 0 instead of 1. Likewise, the second submodel kicks out the 0 people, and it's conditional on answering 1 or 2. My very small logit here of minus 1.3 corresponds to a probability of 0.22. Of the people who answered 1 or 2, only 22% of them picked a 2. And I have that put back together again. Yeah, I knew I had it in here with the table. So putting it all together, the logit intercept of the first submodel gives me the logit of a 0, given that it's 1 or 0, which translates into a probability of 0.61. If I add together the 0's and 1's, that's 0.9. 0.55 divided by 0.9 is my 0.61. So it's like 61% of the 90% is what it means. Likewise, if I add together the 1's and the 2's, that's 0.45. So 22% of the 45% answered a 2 instead of a 1. So everything in these models is keeping some of the cases out of the submodels. They're focusing on only the people who answered those two choices, the reference and the alternative. Stata, though, hides this from you. If you ask for margins to get the predicted probabilities, it's like, here you go, 0.55, 0.35, and 0.1. So it puts it all back together again across the submodels in a way that sort of obscures what the actual submodels are predicting. I'm not sure if that's helpful or not. In R, I am using VGLM. That's the same one that I used for the cumulative logit model. And I learned the hard way through trial and error that R will let you choose your reference category, but it doesn't care how your original data are stored. So it's ref level equals 2 because I want the second choice to be my reference, but in my variable it's 0, 1, 2. Confusing? Yes. Because I started off by putting a 1 here, and the answers didn't match data. I'm like, what? So I figured out through trial and error that that's what it was doing. It's the order of the category, not the number it is stored in as your data. Names of the linear predictors. Log mu1 or over mu2. So this is correct if we replace the 1s and 2s with 0s and 1s, because that's how it's actually stored. So this is probably going to be a lot less confusing if you just stick with 1, 2, 3 as your answer choices rather than 0, 1, 2, because then everything is aligned. Mu, by the way, is another way of saying the inverse link metric you're trying to predict. So in this case, mu is probability. Inside this little set of parentheses here, that's odds. The probability of the target of the model over the probability of not the target of the model. So R is actually trying to help you, just in its own convoluted way. I inverse linked those two logits to figure out the probabilities, and indeed they match. So the 0.61, 0.22. So I'll say that again. The first submodel is telling me that 61% of the 90% who answered 0 or 1 answered a 0. The second submodel is telling me of the, what was it, I've already lost it again, 45% who answered 1 or 2, 22% of them answered 2 instead of 1. There we go. Okay, with me so far? So here's a model with 3 predictors. This will be our last one. How many slopes are in my model and don't say 3? 6 of them. I can tell that based on how I wrote it. Each of my betas has a different subscript for when it's in the model predicting the 0 or the model predicting the 2. I can also foreshadow that in Stata's output by the model likelihood ratio test with 6 degrees of freedom, meaning I added 6 things. So adding the 3 variables we now know and love. Here is the model predicting 0 instead of 1, and the second model predicting 2 instead of 1. It helpfully tells you what the base outcome is, so you can figure that out. So let's look at, say, GPA. GPA has a negative slope. It's non-significant, but it's negative in the first submodel, but it has a positive slope in the second submodel. Does it make sense that a higher GPA would correspond to a lower chance of going to grad school? Probably not. But is this correct, or have I screwed something up? Thumbs up for correct? Why are all of these negative, do you think? They're predicting the zero. That's exactly right. So this one is sort of backwards in terms of our natural ordering. We are predicting who is saying hell no to graduate school. If I have a higher GPA, I am less likely to say hell no to graduate school. So it's like a double negative here. Parent graduate degree has a significant slope. It is also negative, because if my parents have a degree, I am less likely to say hell no. So if I wanted to compare these slopes across submodels, because they differ in their direction of what is higher versus lower, I would need to reverse the sign of one of them before I compared. But if I look at the absolute value of these, to me it looks like numerically GPA has a reasonably similar effect on the first submodel as it does on the second. But that might be something that you're interested in predicting. Does a predictor have more of a say in selecting one type of non-reference outcome than in another? Let's see, what's another one that's, yeah, none of the slopes in submodel 2 here are significant. Any ideas why that might be? Sample size, yep. These are slopes only for people who answered 1 or 2, and that's less than half the sample. So keep in mind differential power for each of these effects as a function of who was in the categories in question in that submodel. I can use LinCom, which stands for linear combination, to test differences across submodels in the size of the effect. Let me zoom in here. This looks different than usual. If I want to test a difference between slopes, for instance, is the effect of number of publications stronger than the effect of number of posters, hypothetically speaking, right? If I wanted to do that, what would a linear contrast look like to do that? If I want a difference in slopes usually. Like what would I put here and here, which corresponds to the zeros and ones in R in the series? If I want a slope difference, yeah, one of them's got to be -1. So in this case, this one would have been -1, but I flipped it because it's going backwards. It's predicting the 0. So it's kind of like absolute value is essentially what I'm doing here, in a roundabout sort of way. So that's why I'm saying this is a slope difference, even though it looks like I'm adding them together, because I reversed the sign of one of them, which ends up making an addition instead of a subtraction. And the results suggest, as I guessed, nope. The difference in the effect of GPA across submodels, once I control for the difference in direction, no difference, not significant. Same thing is true for parent to graduate degree. Private school almost has a difference, but not quite. Can I take these logit slopes and convert them into probability? Nope, still not allowed. Can I take my logit slopes and convert them into odds ratios for other people besides me to learn from? Now this depends on who you ask. In the Stata textbook and in the code, they insist that these are not odds ratios. They are something called relative risk ratios. But you know what? It's the same damn number. So I don't care what you call it, but they make a point of differentiating these. My guess is because of the conditionality of the submodels. They want a different term for that. So rather than saying OR if you want odds ratios, it's RRR, relative risk ratio. And it's RRR in the output. In R, Ref level equals 2 because I'm predicting the second outcome as the reference, second category, let's say it that way, as the reference. Reverse equals true means give me intercepts, damn it, not thresholds. And it has everything grouped by submodel 1 versus submodel 2, where submodel 1 is predicting the 0. So everything agrees pretty much the same with the coefficients. Standard errors are just a little bit off. The same tests for differences in across submodels for the slopes would look like this in R. The only difference is that rather than having the negative one here, I have it as a positive one, again, to flip the sign so that it's consistent in direction. But they come to the same conclusion. None of these slopes differ across submodels. Here's the likelihood ratio test that I would need to do in R that Stata does for me, comparing the -2 log likelihood from the empty model to the model that has my 6 slopes. The model itself is significant, though. Is that surprising, given that only one of our slopes is significant? Think back to regular regression, though. Each of these I would characterize as a unique effect. The idea that this is the effect of whether your parents have a graduate degree after controlling for GPA and after controlling for private. Do you think there's a correlation between these 3 predictors? Quite possibly. So yeah, the model as a whole is significant in the extent to which it predicts this outcome, even though only one of my 6 slopes is significant, because none of them gets credit for what they have in common. It's the same idea. So to the extent that your predictors have a lot in common, they're related to each other, or the dreaded term collinearity, each of these unique effects is going to be weaker. So keep that in mind, that the same principles that you learned in regression modeling for regular outcomes apply for generalized outcomes as well. All right, odds ratios, whatever you want to call it. Predicted outcomes. So Stata, you can do that with margins. Predict XB gives you the link metric. So in Logits, without it, it gives you probabilities. The same thing in R can be done with the predict function. So I'm using the same fake people that we introduced last time. Link is the Logit version, probability is the response version. So then I relabeled the god-awful names that it came up with into something that's a little bit easier to understand. So the first 2 categories then are giving the predicted logits from each submodel, and then R does you a solid and converts those into the probability of each answer category. So at the end of the day, whether you have an ordinal model or a nominal model, all of these models are designed to tell you for a given level of your predictors, what is the predicted probability of each answer category. They just differ in how they get to that point.
I have a question, is that how you choose baseline or cumulative? Because you're saying like if it's ordinal, public goal is cumulative, and if it's nominal, public goal is a baseline model. But then they are not really that different. Like I feel like even when we have the ordinal, like this one, we put it in a baseline, we still get the same result.
In this story, there's only 3 categories, and so yeah, the results are fairly similar. They will diverge in terms of what you would conclude the more category responses you're trying to model. So I think that a baseline category nominal model could be useful even for ordinal outcomes if you really care about each particular outcome. Like if you want to be able to say, what makes someone more likely to say strongly agree, as opposed to agree. Like if you care about each category as its own thing, these models allow you to really isolate that. And you could always change the reference group around across models so that you can get, sort of these all possible combinations of interest to you. But these are designed for nominal types of response formats. So like, let's say that you're taking a personality quiz, and it's like, this happens which of these things are you most likely to do? Like those types of quizzes that they had in like 17 magazine. They have them as indicators of like aggressive behavior. Like somebody trips you on the sidewalk. What do? Ignore it, punch them in the face, call them a bad name, right? Those things are sort of ordered, right? In the sense that punch them in the face is the worst, call them a bad name, and then let it go. But if you're someone who's interested in predicting, like, who is it that's more likely to turn to verbally abusive behavior than physically abusive behavior, then even though you're thinking of this as potentially like an ordered set of choices, like predicting let it go versus yell at them, and then let it go versus hit them, like those would be useful if you're thinking of those as distinct pathways of responding to a situation. So I think that nominal is always useful, potentially, if you care about what differentiates each potential answer choice. The thing that you can't do, though, is take a nominal outcome, like what's the best kind of pet? Clearly the right answer is cat, but not everyone would agree with that. If you try to fit a cumulative model to an answer set of choices that are like cat, dog, bird, iguana, that doesn't mean anything. Like, so that'd be like the one way to screw this up, is to fit an ordinal model to something that is decidedly unordered. But you can fit a nominal model to an ordered if you care about each of the specific categories.
With order model, like what type of function will be like emphasizes on the transition part?
So ordinal models, from what I've seen, tend to be used when you really want to pretend like you have a number that's a number, but you can't. So like if I have a survey response that is, 1 equals strongly disagree, 2 equals disagree, 3 is neutral, 4 is agree, and then 5 is strongly agree. Like you'd be tempted to think of that as a number that you can predict with a regression model, but it's not really. But fitting an ordinal model allows you to treat it as ordinal, but still potentially talk about what is related to a higher response, where you're just saying higher. You're not caring whether, like, which higher it is, right? Because the ordinal models tend to have the slopes constrained equal unless you say so otherwise. All right, other questions? No? Okay, cool. So I made some more pictures. The Excel sheet where I made these is available in the download packet, so you can look at that. I flipped the direction of the pictures so that the slopes were going in the same way. So I have, this is the logit of not versus and then this one is the probability of that. On the bottom, it's the logit of versus very, 1 versus 2, and the probability. And so the same patterns that we've seen hold, in logits, the slopes are straight. In probability, the slopes get bendy. If I want to make predicted probabilities, the order of operations, go from the logit coefficients to create a predicted logit. Take that predicted logit and turn it into a predicted probability. So that the transformation to probability only happens on predicted outcomes, not on slopes. And here's some words. I have SAS output in the download packet as well for those of you who are used to using that. So that's what I use to make most of this. And there we go. So your next homework will give you a chance to practice an ordinal outcome and a nominal outcome. And I promise there's no interaction terms for this one. They'll come back for homework 3 or homework 4, don't worry. But for this one, your job is to figure out what the hell the submodel is predicting, because that is enough. That is enough complexity. All right. Any other questions before I call this one good? Call it done. Yeah?
What would you do in like a nominal if there's more than 4 with like a reference group? Like it makes sense to make like 2 reference groups, but how would you compare?
It is entirely up to you. You just have to designate one, or the program will do it with some sort of default for you.
But you make like 1 reference, isn't it weird to compare 1 to 4?
It's not weird if you remember that the numbers are just labels and they're not numbers. So the way I would think about it is like cat versus iguana. That's not any more weird than cat versus dog. Unless you want to go with like a furriness scale of some kind, in which case it is weirder, but that's where the analogy breaks down. There's nothing that stops you from fitting different models, changing out the reference category so that you can get all the exact comparisons that you want. But at the end of the day, they do get put back together again into a predicted probability of each category. The link function, the submodels, is just a roundabout way of getting there. Okay. Anything else on this? Questions? All right, then I'm just switching gears.